This video focuses on how to find equations that describe the null geodesics followed by massless particles such as photons in the equatorial plane of a Kerr black hole. These equations are of the forms Ct of r and phi of r and are found through integrating the components of the tangent vector to these null geodesics. Right, massless particles such as photons, gravitons, and possibly some neutrinos travel along null geodesics. Now, these are null curves whose tangent vectors are null vectors, magnitude 0. The principal null geodesics in the equatorial plane of a Kerr black hole have tangent vector components of the following form: Ct of lambda, r dot of lambda, Ct dot of lambda. Each of these derivatives here, dt, d lambda, they're a function of lambda, the parameter used to parameterize the path of the particle, to parameterize the world line of the particle. And lambda is the affine parameter used to do that. And the components are, as we found in the video immediately prior to this, are a squared plus r squared times c times epsilon, the energy parameter on delta, plus or minus c times epsilon for r dot, plus being the outgoing geodesic minus the ingoing. And given we're in the equatorial plane, theta is pi on 2, so theta dot, d theta d lambda is 0. And then for the azimuthal angle, that derivative, d phi d lambda, is plus or minus ac epsilon on delta, plus or minus depending on the direction which the particle moves. Lambda is the affine parameter. Now, what we seek are expressions that can describe these geodesics and give us information about these geodesics. We'd like to know the coordinate time of the photon as a function of the radius, as a function of how far from the source mass it is. And we'd like to know phi also as a function of the radius. We could then plot this by projecting it onto the xy plane, and it gives us a visual indication of where the particle is and how it's moving. And that'll happen over the next couple of videos. But before we do, let's come back and start from the beginning. Let's define some variables we'll be using. Mu is g times m on c squared. M is the source mass, and g is the gravitational constant. C is the speed of light. The spin parameter A is gm on c squared times a star, and a star is the dimensionless spin parameter, and it lies between 0 and 1. For this range where a star is between 0 and 1, that means that a squared will be less than mu squared, because this a star is strictly less than 1, except in the extreme case, strictly less than 1. And so that mu squared will always be greater than a squared. And we'll use that and some version of that over the next few slides. Delta is a squared plus r squared minus 2gm r and c squared, or r minus 2 mu r plus a squared. And the importance of that, as we'll see on the next slide, is that when delta is set to 0 and solved, it gives us this quadratic is set to 0 and solved, it gives us the two event horizons, the outer event horizon and the inner Cauchy or inner event horizon. So the outer in red and the inner in green. The outer stationary limit surface is, or surface of infinite redshift, is the yellow one, and the inner version of the stationary limit surface is the blue one. The red dot is the ring singularity. All right, now we want an expression in the form Ct of r. So we start with C dt dr is Ct dot on r dot, using the components from the previous two slides earlier. And that gives us a squared plus r squared c times epsilon, or c times epsilon delta, or just a squared plus r squared on delta. Then we seek an antiderivative of the form Ct of r as the integral c dt dr plus constant of integration. And we now have the integral a squared plus r squared from up here, and the delta was r squared minus 2 mu r plus a squared dr plus the constant of integration. We want to resort to integral tables, and it's convenient in working with those integral tables to convert the denominator, to complete the square on the denominator and convert it into a form where we can readily read from integral tables. There are actual integral tables where you have this quadratic part down the bottom. You can do that as well. But anyway, So completing the square, delta is r squared minus 2 mu r plus a squared. Well, completing the square on that is r squared minus 2 mu r plus the minus 2 mu bit over 2 minus 2 mu over 2 all squared. And what we add, we then must take away at the end in order to keep the expression the same. And when we do that, we have this part here becomes r squared minus 2 mu r plus mu squared. And then the two remaining terms, a squared minus mu squared. All right. Now this part here, the first three terms, can be factorized as r minus mu all squared, and then the two end terms plus a squared minus mu squared, which we will just call alpha for the moment. Now alpha overall is negative because a squared is less than mu squared. So alpha overall is negative. It's just subsumed in there, and that bit of information will be important in the coming slides. Okay, so we now have Ct as the integral, Ct of r is the integral c dt dr integrated with respect to r, is the integral a squared plus r squared on delta dr plus the constant of integration, and substituting in the information from the previous slide, we have r squared plus a squared all over this denominator. Okay, we're going to make the substitution now. We're going to set z equal to r minus mu. So this bit here we'll call z. Z is r minus mu, so dz is equal to dr, the differential of both sides. And rearranging this, we can write that r is z plus mu, so that when we want to deal with r squared by itself, we can have r squared is z plus mu all squared, and expanding that out gives us z squared plus 2z mu plus mu squared. Okay, and so for this numerator here, when we want to write r squared plus a squared, then we have for the r squared bit, the previous result here, plus the a squared on the end. So we have this plus a squared. And so let's now write out the integrand here, r squared plus a squared on r minus mu all squared plus alpha. Well, that becomes this over the denominator, which is, as we've seen earlier, z squared plus alpha. So z squared plus alpha, r minus mu is z, so z squared plus alpha. So we have z squared on z squared plus alpha, 2z mu on z squared plus alpha, and then the constants at the end, mu squared plus a squared, put that together all over z squared plus alpha. So our integral is now this, we can write this out, integrating now with respect to z, and plus our constant of integration. Okay, from the following integral tables, which can be easily found anywhere on the internet, anywhere, but here's your integral tables. Integral x squared on mx squared plus n dx is x on m minus n on m integral 1 on m x squared plus n dx. And similarly for this bit over here, again from the integral tables, where this holds where n times m is less than 0. Okay, and so we'll put a minus here in order to make it positive, so we can take the square root of it. Natural log, absolute value of all this. Okay, and this familiar one here, which we know almost off by heart, x on x squared plus n squared. Well, it's going to be a half natural log of x squared plus n squared. Differentiate this, you have 2x on the original x squared plus n squared, then times a half, so the 2 goes, we're left with x on x squared plus n squared. All right, now let's apply them. So the first one, z squared on z squared plus alpha, well, that's the first one here. Notice here the m is going to be 1 in this case, so it'll be just z over 1, or just z, minus, now the n bit here, remember n times m is less than 0, well, the n bit here is just the alpha. See that n there matches up with the alpha here. Okay, and we have to remember the overall alpha was negative, as I was mentioning on the earlier slide. Overall it is negative, so we'll put a negative in front of it, so we take the square root of it. Otherwise we won't be able to take the square root of it, not unless you want imaginary results, which doesn't apply here. So we've got z minus alpha, which is n, alpha, over 2 times the square root of minus alpha. Remember, n times m is less than 0, negative, so we'll put a minus there. Natural log of this bit here, the n was alpha, the x was z, square root minus nm, which is minus alpha over here. The second bit we had to integrate was 2 times mu times the integral of z on z squared plus alpha. Well, that's an application of this bottom one here, so we just end up with mu times the natural log of z squared plus alpha. And then the last one was the constants. We had mu squared plus a squared all over z squared plus alpha, so let's just put the constants out front. They don't need to play an immediate part yet. So they come out here, and 1 over z squared plus alpha again is this middle integral here. So we have 1 on 2 times square root alpha. In other words, we just have this bit here. Okay, natural log of all of this. All right. Next bit. All right, now we have to remember alpha is a squared minus mu squared. So minus alpha, if we multiply through by minus, we can then write that as minus alpha is mu squared minus a squared, which is now positive because mu squared is greater than a squared. All right, so this now becomes positive by putting a minus sign in front of alpha. Hence, further down here, we can take the square root because minus alpha is now positive, so, which is this object here, and we can take the square root throughout. Okay, so writing out what we have, the integral of all this is all that from previously. Substituting in the things, this one, this one, this one, gives us 1, 2, 3, plus a constant of integration. And then the next bit we have is over here. If we look here, alpha was a squared minus mu squared, okay, but there's a minus out front. So minus alpha, see that minus there, and alpha gives us mu squared minus a squared. So let's put that in there. So we now have a plus here. There was a minus above. Now there's a plus. And this alpha is mu squared minus a squared. So minus alpha, sorry, is mu squared minus a squared. Now if you have a look here, we've got a mu squared over this and a mu squared over this, minus an a squared over this, plus an a squared over this. So they can cancel. The minus a squared and the plus a squared can cancel. And we're left now with z plus mu squared over 2 lots of square root minus alpha, mu squared over 2 lots of square root minus alpha, times the log part as well. And we have 2 of those, so that becomes 1 whole mu squared on the square root of minus alpha, natural log of the absolute value of all this, plus also this third term here, plus the constant of integration. Okay, what can we do now? Next line down, the alpha here as the argument of the natural log is we can now substitute alpha in is a squared minus mu squared, so a squared minus mu squared. Substitute that in there. Okay, and here alpha, we'll substitute that in as well. And then what we'll do here, next line down, is we'll just rearrange it to put and then factorize it. So we have a minus outside of mu squared minus a squared. So if we expand it out, we just get the line above. All we've done is we've factored this. Minus mu squared minus a squared in parentheses, expand it out, you'd have minus mu squared plus a squared here. Okay, now you notice we put very similar form here, mu squared minus a squared, and then under the radical sign here, under the square root sign, you have mu squared minus a squared. Okay, and we've done a similar thing here for the last term, z squared minus mu squared minus a squared, plus a constant of integration. Okay, next bit. So we got z plus all this. Okay, that just rewriting the last line again, just so we can compare it. So next line down now, what we're going to do is we have here, we've taken out a common factor of square root mu squared minus a squared from the top there, and also from the bottom, and they cancelled. So we're now left with just the z by itself here, and one factor. Remember, this can be broken into 2 factors of square root mu squared minus a squared multiplied by each other. Okay, take that one out, take one out here, divide top and bottom, so they're gone, and we're left with just this. And on the right hand side here, we can write this as z squared minus the square root of mu squared minus a squared all squared. And that still gives us this term here, so from here to here. Just a different way of writing this. Okay, next step then is the next line down, we'll take the z and put it out front here, and we'll take the z here, minus z minus that. And then here, we will write this out, difference of perfect squares, z squared minus this object squared, so that becomes z minus the object times z plus the object. Mu out front, constant k. Now we're going to substitute z is r minus mu. So where the z is, everywhere here, we're going to put r minus mu. So here, r minus mu for that z. And then r minus mu in here, minus r plus mu as a result of that. r minus mu minus all that. Okay, and there plus k. And then next line down, r minus mu, all that. And pull this out here. And then this bottom line, I'm just going to pull out that factor of -1. Okay, just that -1 out there. Right is r minus mu plus all that. Okay, mu, natural log, all of this. Okay, next page over. Here we go. We've got r minus mu plus this, that. See the minus here? That disappeared because of the absolute value sign there. Okay, it's the absolute value of what's in there. So I could have had on the previous slide down the bottom there -1 times all of this. And then the absolute value will take care of that -1 and remove it. Okay. Next bit now, plus this. Here we go, plus a constant integration. Now, if you remember the outer stationary limit, the outer, event horizon and the inner event horizon, r plus was the outer, this. R minus was the inner. Then we can write r minus r plus is r minus r plus, all this. And r minus is r minus and then the negative of all this, so minus mu plus square root of that. And if you have a look in here, this one up here becomes r minus r plus, r minus r minus. And here, this becomes r minus r plus. This becomes r minus plus the k. And now the expression's starting to simplify a little bit. Okay, we can now use the log laws because this object here can be expressed as the natural log of this minus the natural log of the bottom bit, the denominator. Okay, and same over here, we can use the log laws here. It becomes the natural log of r minus r plus the natural log of r minus, and then we still have a constant of integration there. Okay, so we can start to combine things. Go to the natural log of r minus r plus here, natural log of r minus r plus here, and then similarly for the minus case. So we can combine those. And when we do that, we can combine it like this, plus the constant of integration. Now, in the next line down, what happens is that a number of textbooks quote the final result as this. And what they've done is they've taken this constant here, because mu is just a constant. They've taken, once you know the value of A, mu is just a constant, and the mass and the gravitational constant and so on, it's just a constant. You can absorb that constant into the n one here. So I'll go from k to k1. I've got a new constant called k1. All right, so here's the end result, where this minus mu has been incorporated into that constant on the end. So we can describe finally the relationship between coordinate time and coordinate radius by CT as this. Okay, and where K1 has absorbed that constant mu there, minus mu. Okay, so that's that first one. And next we seek a relationship between phi and r. Well, r dot was dr d lambda is plus or minus c times epsilon, plus for outgoing geodesic, minus for ingoing. Phi dot is d phi d lambda, plus or minus again, because it depends on which way the particle co-rotating or counter-rotating, so prograde or retrograde. D phi dr is then phi dot on r dot is plus or minus ac epsilon on c epsilon delta, so it's plus or minus a on delta, plus or minus a on all of that. Remember we found delta earlier could be written in this form here. Next bit, seek an antiderivative of the form. We want phi, the azimuthal angle, as a function of the radial coordinate, is the integral d phi dr plus k2. So we have this object here plus that, gives us this object. K2 is our constant of integration. Now, from the integral table, because it's a constant over this, we use this one. So I won't go through all that again. Remember, n here is the alpha, m is 1 in this case. Remember, alpha is a negative object, and so we have to put a minus in front or take the square root. So the integral of a on z squared plus alpha is 2a, applying the integral here, that's 1 over 2 times, remember, minus nm is just minus alpha. Minus alpha is this object here. We have the a here, so that goes there. So we have a on 2 square root mu squared minus a squared. Natural log, the absolute value of all this, plus k2. See all this? N was alpha, okay? And as before, so we have this object here. Same thing again, we'll take out a factor of this, square root mu squared minus a squared. Remember, there's two of those factors in here. And same, so we, similar to what we did before. Then with the z's, we'll substitute r minus mu. So plus z r minus mu, and this bit here. Again, this overall negative result here will resort to the absolute value sign to clear that for us. And we're left with this object here. Again, we'll use that minus to clear that. And we end up with r minus r plus on r minus plus the constant k2. And so our second result is phi of r is a times a over 2 times square root of mu squared minus a squared, natural log of that, plus k. We could separate those out, but there's no need to. I'll just leave it in that form. It's more compact rather than use the log laws and have a second log over here with minus. Just one last thing before we finish. Notice that in the limit as a approaches 0, we end up with the radial null geodesics of the Schwarzschild geometry. Those equations are CTR plus T mu ln, where a goes to 0, a lot of things drop out. See here, a goes to 0 here, and phi of r just becomes a constant because in the Schwarzschild geometry you can have purely radial paths where a particle with or without mass can come in a radial direction. There's no rotation, so there's no twisting of space-time. A particle can come in on a pure radial path, so a pure radial path then has a constant angle. All right, and that's it.